So in this section, we will look at the rotor. In the previous one, we looked at just the stator with rotor open circuited. But in this section, we'll look at rotor as well as simultaneous excitation of both stator and rotor. So we know that most induction machines have squirrel cage rotor, but for the analysis that we want to perform, we will represent this squirrel cage rotor by equivalent windings, and it's most convenient to think of them as three-phase windings, as it's shown here. And we'll also, it's arbitrary as to number of turns per phase for this rotor, but I think most convenient is to assume that the rotor has the same number of turns as the stator, n sub s turns per phase as in the stator circuit. Okay, so that's what is shown here. And so the rotor windings are represented by these three phases, A-axis, B-axis, and C-axis. And it is assumed that each of these windings are sinusoidally distributed, just as it was the case in the stator. Okay, and we assume that the currents are going in, and I think there may be a mistake. No, it's not a mistake. This is the stator circuit, and so when the currents go in, the magnetic field produced is along that axis in the radially outward direction. And the same thing we'll assume for the rotor circuit, but in this case we have currents IA, IB, and IC, and so in a squirrel cage, the currents going into one direction cancel out or add up to zero when you include the currents going in the other direction. So this connection of the neutral, this dotted line that I have shown here, is really not necessary. What I'm trying to point out is that some of these three currents in the rotor circuit, just like in the stator circuit, will also be equal to zero. Okay. So now let's look at the rotor winding inductances. And in this case, the stator is open circuited. And so we should note that the magnetic path that flux has for when we excite a rotor phase is the same as it is when we excite a stator phase. So it's no surprise that the magnetizing per phase magnetizing inductance and the single phase magnetizing inductance for the rotor is the same as in the stator case. Okay, the only difference is that the leakage inductances may be different. So when we define the self-inductance of the rotor phase is, we'll talk about the self-inductance of the rotor, leakage inductance, I should say, leakage inductance of the rotor, L sub Lr. That may be different than L sub Ls, but L sub M is the same. Okay. So, this is interesting here that our choice of n sub r equal to n sub s results in these this inductance, let's see, L leakage, which is the same as what we see in the per phase equivalent circuit in the previous course, Lr prime, and R sub r that shows up is the same as R sub r prime in the equivalent circuit seen from the stator side in our previous course. Okay, so now let's look at the mutual inductances between the stator and the rotor phase windings. Yeah. So we can see here that in this figure that is shown in the right-hand corner is if theta sub m is 0, the rotor A-axis is on top of the stator A-axis, and in that case the flux linkage between the rotor A phase and the stator A phase is the same as Lm single phase that we had calculated, because the same magnetic path, right? And whatever flux is there is would be the same whether it's rotor or stator. So the mutual inductance between the two is the same when you have both these axes for phase A of the stator and phase A of the rotor on top of each other. But if they're at an angle theta sub m, as is the case, then I think this leakage inductance between the stator, mutual inductance I should say, not leakage, mutual inductance between stator A phase and rotor A phase would be this Lm single phase times the cosine of theta sub m as is given here. And the same would be the case for mutual inductances between any of the stator phases and any of the rotor phases. You have to take the angle between them into account. Okay. And it clearly shows that this mutual inductance you have between the stator and rotor phases, this mutual inductance is dependent upon this position theta sub m here. Okay. So we'll make use of space vectors. It makes our analysis much simpler. Otherwise, there'll be long equations to deal with here. So let's very briefly review the space vectors. And we had in the previous course talked about MMF space vectors. So when you have current in phase A, for example, is producing this MMF space vector F sub A, and space vectors we indicate by putting an arrow on top of them. And so it's really the flux, MMF distribution in the air gap, which is sinusoidal, but it's being represented by a space vector. Same thing when you have current IB, it's producing this MMF distribution represented by FB and FC here due to I sub C here. And then to find out the total MMF distribution in the air gap, rather than having to add them point by point as a function of the position, we just need to add these three vectors vectorially, and we get this F sub S as MMF space vector, which has an amplitude and has a phase angle theta sub Fs as shown here. Okay, so that's really kind of the review, and mathematically is written as I described earlier, the vector sum of these things here, right? So, so it kind of provides a physical basis for understanding space vectors when you're dealing with distributions, okay? Because when you're dealing with distributions, the implication is that they are sinusoidally distributed in space as a function of theta in the air gap, but we are representing them by a space vector. Okay, and I should point out that unlike phasors, space vectors are applicable under dynamic conditions. They work under DC conditions because the sinusoidal distribution is provided by the windings being distributed sinusoidally. So that's the reason. Okay. So when it comes to terminal quantities like current, voltages, and flux linkages, what we'll do is we'll just take at any instant of time t, any instant of time, whatever that current, those currents happen to be in these three phases, we will multiply them by their axis orientation. So IA by e to the j0, which is the reference axis, then 120 degrees, and then 240 degrees here, and that gives us the resultant current space vector, and we put, and that is represented by this subscript S. So that's the stator resultant current space vector, and this A here indicates that this is being represented with phase A stator axis as the reference. Okay, so that's important to note that this superscript A indicates that it's with respect to stator A axis as the reference. Okay, because any complex number you define, it has to be defined with respect to some reference. Okay, and so at any given time, this I sub hat is, let's say, is the amplitude, and the phase angle theta sub is where the space vector lies. And this exactly the same thing we can do for voltage, where each individual phase voltage is multiply its respective phase orientation, and then we come up with the resultant stator voltage vector, and similarly we do for the flux linkage here. Okay, so there's no difference between the three. And it's very difficult to give any physical meaning to voltage space vector and flux linkage space vector, but we can give a physical interpretation to the current space vector, which is very useful, I think. So we know that MMF space vector and the current space vector, they are related by this coefficient here, ns over the number of poles. So what is the meaning of this current space vector at any given time? So let's say that at some time the current space vector is over here, okay? And here we don't have to put subscript a here because it's obvious that this angle is being measured with a-axis as the reference. Okay, so what is the physical interpretation of this? What it's telling us that the MMF that is produced by these three currents simultaneously, IA, IB, and IC, the MMF produced due to all three currents flowing simultaneously is the same as if this MMF is produced by a hypothetical winding which has the same number of turns as any of these windings, n sub s, same number of turns, but its axis orientation is in the direction of this is space vector here. And the current that is flowing in this sinusoidally distributed hypothetical winding, that current peak is is hat. Okay, so I shouldn't even say current peak. Current peak is the peak of this is space vector, but that is the current that is flowing through here. And again, this is sinusoidally distributed, this hypothetical winding, and therefore the circles are of different sizes over here. And you can clearly see that the magnetic axis is along here, which is the same as the axis of this current space vector here. So that is really the physical meaning. And this physical meaning kind of permits us to visualize the stator current space vector, and but it also very much simplifies the derivation of electromagnetic torque. So now instead of calculating the electromagnetic torque in each of the phase windings and then adding it up, rather what we can do is we can calculate the electromagnetic torque in this hypothetical single winding. Okay, so the important thing to recognize is that it also has the same number of turns as any of the phase windings, and it is also sinusoidally distributed. Okay, and the similar space vector equations can be written in the rotor circuit with its rotor phase A winding as the reference. Okay, so in this case, A, uppercase A, is the reference winding in the rotor here. Okay, so this equation I think we have seen before, and so maybe it's really not necessary to talk about that. Just like the currents, we have voltages and flux linkages, and they can be represented by these space vectors over here. Okay, so it'll be interesting it is interesting to look at what happens when you have currents only in the stator windings and rotor is open circuited. So when rotor is open circuited, you can see that the flux link resultant stator flux linkage due to this current is now, which is really made up of IA, IB, and IC, you have a term which is due to the leakage and the current flowing in I sub A, and then you have this mutual inductance L sub M and the current in I shouldn't say IA. I was wrong. It was stator current space vector with respect to A axis and stator current space vector with respect to A axis again here. So let's just be clear here. I made a mistake by saying that you have this flux linkage, stator flux linkage space vector due to the currents in all three phases, IA, IB, and IC, adding up to 0. okay, that can be represented as leakage times the stator current space vector plus the magnetizing inductance times the stator current space vector. And then we know that Ls is equal to the leakage plus L sub m, so we can write this expression here. Okay, and this is being written with rotor open circuited, and all the quantities that result, the current space vector, the flux density space vector, the MMF space vector, the flux linkage space vector, they're all collinear because the rotor circuit is open circuited. All right, so now we'll do the same thing. Well, what's the difference between the rotor and the stator? It's the same thing. So in this case, we have currents in the rotor windings, but stator winding, hypothetically somehow, is open circuit. Okay, so here you see that a very similar equation as before shows up, but it's respect to phase A of the rotor winding here. Okay, and here in this case you have the rotor current space vector that is causing this flux linkage in the rotor circuit, and again knowing that this rotor self-inductance is the leakage of the rotor plus L sub m, which is the same in the stator. All right, so now what happens when we have simultaneous excitation both in stator and rotor? This machine is really no good if excitation is only in one and not in the other. So let's take a look. So if you look at the flux linkage for the stator, we saw early on, well, we haven't seen this before. So what's going to happen is that this is due to both the stator current space vector and the rotor current space vector, but they all have to be defined with stator a-axis as the reference here. So you see the subscript a here, okay? And we have to recognize that this current space vector, rotor current space vector with respect to stator a-axis is not the same as the rotor current space vector with respect to rotor a-axis. There is an angle between these two axes, so that shows up over here. So when you plug in for this here from this equation over here, what we get is this equation here. And what we see immediately that this flux linkage of the stator is dependent upon the rotor position, theta sub m, right? So theta sub m, okay? And so the same thing we can do for voltages too. So if you write the voltage for each phase, what is voltage in phase? Any phase, it's equal to the voltage drop across the resistance times d lambda dt. Okay, so we write it for phase A, and then we write it for phase B, and we write it for phase C. And in order to get the space vector made up of these three voltages, we multiply them by individual axis orientation here, right? And then we add them up. So when you add them up, you get this stator voltage space vector, and then the drop due to the stator space vector current, and then also dt of this flux linkage space vector. And we can do the same thing for the rotor, no difference. So you have this resistive drop, you have this ddt term over here, and since if the rotor is a squirrel cage rotor, each of the phases in this equivalent three-phase winding representation, the voltage across them is zero, and their sum would be zero as well. So if really it's a squirrel cage machine, then this term here is equal to zero, as indicated over here. But if it's a doubly fed induction machine, then this could be whatever it is, but not zero, perhaps. Okay, now we come to make the case for a DQ winding analysis. So what we have done so far is to get ourselves ready for analyzing this machine in these ABC reference frame. But what we would like to do is to say that really we shouldn't be going too far with that ABC reference frame, and we should go to something called DQ reference frame, which we'll look at later on. That's the topic of the next chapter. Okay. So why should we do that? That's the case we would like to make here. So you see that the current in the rotor current space vector with respect to stator A-axis and rotor A-axis has this angle over here. Okay. Similarly, the stator current space vector with respect to rotor A-axis and with respect to stator A-axis has this angle over here, right? So using these two equations, we can see that the flux linkage is given by this expression, which has this rotor position dependence over here, and similarly, the rotor flux linkage space vector is given by this equation, which has this rotor position dependence over here. Okay, so if you use these equations in voltage equations here, of course they will have rotor position dependence over here. So it becomes somewhat complicated, not impossible, but somewhat complicated, and it certainly can be done. But the point is that it doesn't give us the physical intuition how to control these machines. What we'll do is we will go to this DQ winding analysis in the next chapter, and we'll see that by controlling the current in one axis, Q axis, we can control the torque in this machine, and by controlling the current in the D-axis, we can control the flux. And these are sort of independently controlled, so it becomes a very easy and decoupled control, which is not easy to see in this ABC quantities, phase quantities. So let's stop here, and then we'll begin with chapter 3 in the next section. Thank you. So got through, David.